Hello everybody. Time for my last video for this batch of assignments. And all the videos I've been making over the past week or so have been leading up to this one, okay? So we learned about something called the instantaneous rate of change. And then after that, we learned that the derivative is a formula or a function that tells you the instantaneous rate of change. And now I want to just do application problems that I would hope would allow you to understand everything that came before a little bit better. Okay? So, like both of these problems, I've set them up and I've created them so that the situations are not real bizarre or they don't take some advanced understanding of economics or science or anything like that. They're fairly basic. Uh, the concepts aren't wild. So hopefully there'll be a way I can show you what I want to show you about how we use the derivative, how economists use the derivative, how scientists use the derivative. Everything I say here can be generalized to anything else, okay? All right. So my first scenario that I want you to think about is imagine that there's a leak in the ceiling and we put a bucket to catch the water that's leaking, okay? So we have a large enough bucket to hold whatever amount is leaking into it in our problem. And over here, I've created a graph, okay, that charts the quantity of water in the bucket as a function of time. All right. Now, I mean, if I'm aware that if you had a leak in your house and you put a bucket under it to catch it, you wouldn't create a graph or measure anything. But like I said, I was going to create real everyday common scenarios and then put the math on top of them. Okay. So, all right. I mean, you could do that. That's what I want you to realize is you could measure the amount of water leaking into a bucket over time. All right. I mean, it's doable. Okay. So look at it like this. Here's the data that's in the graph. So I've got time t on the horizontal axis, okay, in hours, and I've got quantity q on the vertical axis in gallons, okay. In this point, 1 comma 0.5 says at the 1 hour mark, there's half a gallon of water in the bucket. In this point, 2.5 comma 1.25 says at the 2.5 hour mark, there's 1.25 gallons of water in the bucket, and so on. And it kind of looks like water's leaking into it right here. And then we get to that point and the leak stops and the bucket remains as full as it is at that point in time. So that's why at the 4 hour mark, the bucket's still just sitting there and it still has 1.25 gallons of water in it. All right, so that's the function that we're given, Q of t, Q being the amount of water in the bucket at time t, okay? And then I have some questions about what we could say about that function in terms of calculus and the derivative. All right. So Q of t, yes, is the quantity of water in gallons in the bucket at time t in hours. What would Q prime of 1 mean and how would we calculate it? Okay. Well, that apostrophe right there, that indicates that it's the derivative. Okay. And so I want to know what is the derivative of this function q at the time when t is equal to 1. All right, well, so here's what we'll think. We'll say, well, one interpretation of the derivative is that it tells you the slope of the curve or the graph at for any value of the variable. Okay, so q prime of 1 means the slope of the graph or curve at time t is equal to 1. Okay, well, that is just a line. You see right there where t is equal to 1, that's this point. Though the derivative q prime of 1 would tell you the slope of the graph right there at that point. Okay, but that is just a line. And so if the derivative means the slope of the graph, and if the graph at the point we're looking at is a line, then we would just use the rise over run formula. So right here, this part, okay, that is just rise over run. And that's really at the heart of it what the derivative is anyway, okay? All right, now, so how would I find the slope of the curve here? Well, it's a line, and you see the line has this point on it, 1 comma 0.5, and it's got another point on it right here at that knee, 2.5 and 1.25. We can use those 2 points to find the slope of this line right here. See? Okay, so we take 1.25 minus 0.5, that's the rise, and 2.5 minus 1, that's the run. That's the slope of the line formula. Okay, and I get 0.5 for that number. Now remember, in the case where we have like a real function that measures something about the world, whether it's a revenue function, that's one example I've used, or this one, that a function that measures how much water's in a bucket. There are units that go along with the variables. Now, up here, that's the rise. So I was subtracting the y coordinate, so to speak, which actually in this case is quantity Q in gallons. All right, so that number on top has units of gallons. Or like the number on top, I have units of whatever this variable is. So like I said, what I say here can be expanded to apply to anything. So like whatever the units of this variable are, that's what the units are on top. And then down here I did 2.5 minus 1 because that's the run, and so that would be the subtraction of the x coordinates, 2.5 and 1. But I don't have an x coordinate, I have a time or t coordinate, and it's measured in hours. So the units on the bottom are hours. So that number 0.5, that means, or it has units of gallons per hour. Okay, so what does it mean then? There are some questions on the assignment that ask you to select the meaning or interpretation of a derivative or a function. Well, it just means that for every hour of time that goes by at this, from this reference point, the bucket will fill up by another half of a gallon. Okay, the amount of water in the bucket is increasing 0.5 gallons per hour at the time t is equal to 1. All right, so that is our interpretation for our number. So I got the derivative, I told you the number, I told you the units right there, gallons per hour, and gallons per hour means that it's filling up by half of a gallon per hour. Okay, now I did say that this could be generalized to anything, so sometimes you see things like this that I'm about to draw on here. Here we go. Okay, so let's see, like it's like the rise and the run are such like this. Okay, that this was 1 and this was 0.5 proportionally. So like the slope of this, see this line segment is such that if you increase time by an hour, you'll increase the amount of water in the bucket by half of a gallon. See, because we got that from rise over run. So that's why we can put that interpretation back on the number. Okay? All right. So those are all the varied but similar ways that you can think about the derivative once you calculate it. What about this one? Can you calculate q prime of 3? Well, okay, let's see. 3, that would be, I mean, that point's actually not labeled, but, you know, this is 2.5 and that's 4. So, you know, I mean, maybe like right there or so. Okay, so this is where t is equal to 3. But yeah, I don't have a point that's labeled. I can't use any numbers there. But isn't the slope here the slope over here, or the slope over here? Like, you know, this is all part of a line that looks to be horizontal. You know, right there, the line's horizontal. Right here, the line's horizontal. You know, anywhere on that part, the line's horizontal. Just such that anywhere on this part, the slope is a half. Anywhere on this part, it's like if time goes up by 1, quantity goes up by a half. So even though this point's not labeled, I don't need it. It's because, like, if I could just tell you the slope of this line at all, that would be my answer. But here, do you see how that's 1.25? And do you see how this is 1.25? The bucket's not filling up anymore. This line is horizontal. Okay? So the slope of the graph right there is 0 because the horizontal line has a slope of 0. So we'll say q prime of 3 is equal to 0 gallons per hour. And it has a similar interpretation over there because this kind of interpretation for the derivative is universal. Like I said, it could be applied to anything. So, no matter how much time passes at that part of the graph, the water in the bucket increases by 0 gallons because it's not filling up anymore. All right? Okay. So now, whenever I think of this kind of thing, whenever I think of the derivative, I think of something that I hear in everyday life. So I sometimes I hear things like I hear like realtors and so on, or a lot of other people say that for every so and so dollars, so and so additional dollars that your loan increases by when you buy a house, your monthly payment will increase by so many other dollars. Okay, something like that. Okay, maybe you've heard that kind of thing too. For every additional $10,000 that you mortgage, your monthly payment increases by so many dollars. Okay, so maybe you've heard that. I know I've heard it at least a few times recently that I can remember. But that, like, before I even show you my next example, seems like this. It seems like there's some graph or something, and over here is your monthly payment, and over here is the amount of your loan or the price of your house or whatever. And as this goes up by so many thousands of dollars, your loan amount, then this goes up in the same way that you're seeing here by so many dollars per month or something like that. Okay, so it almost sounds like it's just like this. And in truth, it is like this. It's like same idea, just different scenario that I've already compared to what I've already just showed you. Okay, because I said this has like universal applicability to almost anything. So now I want to show you that. Let's apply this to a loan that is amortized, such as a mortgage. Now, so let's bring. I want to kind of present this scenario to you in a way that's appropriate for our class, though. So, say you want to know your monthly, and this is just principal and interest payment when you buy a house. Now, I know your monthly payment typically might include property taxes and insurance and so on. All right, but let's say like just the principal and interest on the loan. That depends on the loan amount. Okay, it depends on the interest rate periodically, whatever the periodic rate is, and it depends on the number of payments. And here's actually the formula. Okay, M, the monthly payment, just your principal and interest, is P times I over 1 minus 1 plus I to the minus n power. Okay, and if I is given as an annual rate, as it typically is when you buy a house, then we use I divided by 12. Okay, because I has to be the periodic rate. But anyway, okay, and this is actually something that if you could look up in our ebook that comes with MyMathLab, that there's a section in the book that explains how loans are amortized. And to amortize a loan is to just divide it up into a series of equal monthly payments that ultimately pay off the loan. Okay, so here goes. Suppose that, now here's the scenario that I want you to think about in this context. Okay, I'm not actually going to use this formula because using this formula is somewhat complicated if we're going to do actual calculus with derivatives, but I've done some of the math for you already, and I just want you to interpret a few things. Okay, at some point for the next test, we probably will work with this formula and apply the rules of calculus to it and see what we can find out. So suppose that for a given loan, I, the periodic rate, and N, the number of payments to amortize it, are fixed. So we've decided that. So it might be that we're going to take a 30-year loan, which would be 360 equal payments at an interest rate of, I don't know, 6%. Let's say, okay? So that's fixed. And the only thing left unknown is P, which is the amount that we're borrowing, the loan amount. Okay, this leaves P as the only variable for M, the monthly payment, whatever that is, to depend on. Okay, now suppose that I develop some formula, M of P, some function, the monthly payment as a function of the principal, that calculates for you what the monthly payment in dollars is resulting from a loan of $1,000. Okay, then suppose I give you these numbers and I just ask you to interpret them. Suppose that I've done the calculations and I calculate M of 225 is 1360, and I want you to tell me what that means. And M prime, the derivative of 225, is 6.05. All right, so what does that mean? That's what I'm asking you. I'm not asking you how I got these numbers. We'll worry about that on the next test. Now I just want you to tell me what it means. So what this means, it comes right out of the meaning of this function. The function M of P tells you what your payment is if you know what the loan amount is. Okay, so in this case, it would say the monthly payment for a loan of $225,000, because I've said that the interpretation of P is $1,000. Okay, but it means that the monthly payment for a loan of $225,000 will be $1,360. Okay, all right, that's all that means. So that's the first thing. How do you interpret the meaning of the function? The second thing, how do you interpret the meaning of the derivative? What does M prime of 225 being 6.05 mean? Well, so derivatives tell you how two variables change together. For example, the derivative of this function tells you how, if time were to increase, how the quantity of water in the bucket would increase. You could say that tells you how fast the bucket is filling up or how fast the water is leaking into it. Whatever, you could say that the derivative tells you the change in this variable P on the bottom and the change in this other variable M on the top. Okay, but no matter how you see it, in this case, it's going to tell me that from a starting point of $225,000, each additional $1,000 borrowed will increase the monthly payment by $6.05. Okay, that's what it tells you. So how does 6.05 tell you that? Well, I mean, it's rise over run. However you want to interpret the derivative, there are many ways, but they are all dancing around the same idea. I could say, well, it's rise over run. I could say 6.05. That's one number. That's not a fraction. Well, okay, it's 6.05 over 1. That means if the run is 1, the rise has got to be 6.05. Okay, what do we mean by a run of 1? Well, that's like the variable P is the run. So if P were to increase by 1, okay, what does that mean though? What is P? P is measured in $1,000. Okay, so if P increases by 1, then that means that we say $1,000. So if P were to increase by 1, that means that it increases by $1,000, increasing the amount that we borrow by $1,000 will cause this other variable M to increase by $6.05. But that other variable is the payment. So if you run by 1, you have to rise by 6.05. You might also see this said is that P changes by 1, M will change by 6.05. That way, in the delta notation, delta means change. So sometimes people write that. Same thing though. Same thing as rise over run. Okay, so that's how we can figure out the interpretation of any derivative. Okay, so you might say if y equals some function of x, so my variables are x and y, then the interpretation of f prime of x is going to be the change in y over the change in x. Y is going to be the rise, x is going to be the run, and from that you can interpret anything. So if you saw something on the assignment or on the quiz or on the test and it wasn't this exact same scenario, this, this general statement about how do you interpret what the derivative does or tells you, or if you get a number and you want to know what it means, it all comes from this right here. Okay. All right. Now, because this is calculus for business and social sciences, we'll be using a lot of business applications. So I thought we would explore this one in a little more detail, because I did talk about that first problem, that the derivative is the slope of the curve. So I wanted to tie that in here. The numbers I was actually using when I did the math behind the scene here, because I said, don't worry how I got 225 and 1360 and 225 and 6.05. But the numbers I was actually using is the N was 360, so that's 360 payments. That's a monthly payment for 30 years. Okay, so it would be like a 30-year mortgage. And then I was 6.08% yearly. Okay, so those were the numbers that I decided to use in order to get those numbers. Now, when we found that the derivative M prime 225 was 6.05, and I said, well, it's like the run is 1,000 and the rise is 6.05, then if you're visual, then you could think of it like I did with the graph in that first problem. Okay, so if this would help you, it'd be great. Here's the plot. This will plot how much I borrow versus what my monthly payment is. Like the graph would actually look like that with these numbers. Okay, and with me finding the derivative to be 6.05, then it's doing what in terms of the graph? It's telling me the slope of the curve. Okay, so this line, right? I know it's not really a curve; it's a line in this case. But what it's telling me is that, okay, see that line right there that plots my monthly payment versus how much money I borrow, that is such that if we go up by 1 on the graph, here we go up by 6.05. Okay, now for my interpretation I'm putting on that, we were measuring P in thousands of dollars. So up by 1 actually means up by $1,000. And we were measuring M in just ordinary dollars, so it means M is up by $6.05. All right, so now do you maybe see in a different way if you're visual that, yeah, this derivative right here, it means from this point, okay, $225,000 mortgage, that, yeah, me borrowing an extra 1,000, the P, the loan amount going up by 1,000 causes my monthly payment to go up by $6.05. Okay. Anyway, so that's just another way of seeing what I already told you. Now, it turns out that now here's like some fine print that we'll talk about a little bit more in the future for the next test. But why the 225? It's actually the case that no matter where you are on this line, it doesn't have to be by this reference. Going up by 1,000 causes your monthly payment to go up by $6.05. Okay, that's the way it works. Whether you're here or whether you're here. Whether you're at 225,000 and you wonder what happens if I borrow an extra 1,000, or whether you're over at 400,000 and you're wondering what happens if I borrow an extra 1,000, what's going to do to my monthly payment, doesn't turn out to matter, because this is a line and the slope is the same anywhere. The time when this number would become more important is when the graph is not actually a line and it has a curve shape to it. So we might find out that certain revenue functions have a shape like this, where this says like a small increase in production will cause a relatively big increase in revenue. So the slope right here is different than over here. So to compare these two places on the revenue curve, then here, yeah, it's like if I increase production this much, I'll increase revenue this much, okay? But then here, if I increase production by this much, then I increase revenue by this much. So this is what I think the economists would call diminishing marginal returns. So at this spot on the curve, we're increasing production by quite a bit and not getting nearly as much increased revenue in return, all right? Over here, increasing production bumps up revenue by quite a bit. Here, not so much. So in the situation like this, it would really matter where you are finding the derivative at. So like here, r prime is big. It's a big number. And over here, r prime is a small number. Okay? It depends on where you are on the curve. Now, if the curve is a line, it doesn't matter whether you're at 225 or anywhere else. So in this case, we would just say m prime of p is equal to 6.05 everywhere. But as we go through the class, we'll see more and more situations where we have functions and we have curves that are different than that and have a different derivative at different points.